Hi, welcome to Algebra 2 Common Core. In this lesson, we're going to take a look at an application problem of exponential functions, one that actually you're probably pretty familiar with because we've done some examples of this before, but now we're going to officially look at the pieces of this kind of function. This is called Newton's law of cooling. Now, the first thing you have to make sure is that you have your graphing calculator right with you because we're going to be using it throughout today's lesson. So if you don't have it, please pause the video and go get your graphing calculator before you continue on. So first of all, we can find, we know that the temperature of a cooling liquid in a large room, and it doesn't have to be a room, it could be outside, it could be in your house. The room has a steady temperature. This is going to be an example of an exponential function that we say is transformed. So we've taken a look at some translations of exponential functions, and this is going to be one example of translated exponential functions. Today we'll take a look at how we can analyze the temperature of the liquid using Newton's law of cooling. So first of all, inside the box you see the formula for Newton's law of cooling. Now usually you're going to be given this formula, but it is probably going to be wise to know at least how to use this. So let's look at the pieces here. Again, you might need to pause the video so that you can write down what each of the variables stand for, but I'm going to talk you through it as well. T of T stands for the temperature of the liquid after T minutes. Now I know that I wrote liquid. It's not necessary that it's a liquid. Sometimes we'll see this formula applied to solids as well, but it's most commonly applied to liquids. T sub S, so that subscript S, stands for the temperature of the surroundings. T sub O stands for the original temperature of the liquid. Usually it's going to be a warm liquid or even solid, and it'll be cooling off because it will be going toward the temperature of its surroundings. Think about a cup of hot chocolate at the ice rink. You know that your hot chocolate is going to cool down pretty quickly if you're at the ice rink versus if you're sitting in front of your fireplace in your living room. K is the decay constant in our formula. Now the other thing that I want to point out here is that we're going to be using an exponential most often with a base of e. It's not necessary that it's a base of e, but that's the formula that we're going to be looking at today. We've seen some examples of Newton's law of cooling where we've also made the base be a number other than e. So it is possible to use a number other than e. So for our first example today, we're going to talk about a pot of tea that is heated to 90 degrees Celsius. Notice that this problem is completely done in Celsius. A cup of the tea is poured into a mug, and it's taken outside where the temperature is 18 degrees Celsius. So obviously the tea is warmer than its surroundings. After 2 minutes, the temperature of the cup of tea is approximately 65 degrees. So we can see that the tea has cooled off as we brought it outside where the temperature was cooler than the original temperature. Determine the value of the decay constant K, round to the nearest 10,000ths. First thing I'm going to do is identify some of the information that I'm given according to my variables that we saw on the above formula. So the first thing we know is that the pot of tea is heated to 90 degrees Celsius. So that is going to be the original temperature of our tea. So I'm going to label that T with a little subscript of O. The outside temperature is 18 degrees, and that's where we now have our tea. So I'm going to call that T with a subscript of S. Now we also have some information that after 2 minutes, the temperature of the cup of tea is 65 degrees. So that means my formula T of 2, so the temperature at time 2 of the tea, will be 65 degrees. And that's going to come into play in our problem as we solve for our decay constant K. So the first thing I'm going to do is set up my formula using the formula from the box above. So I'm going to say T parentheses T. So don't get confused with the two T's there. Little t stands for time, capital T is standing for temperature, is equal to the surrounding temperature. So I'm going to start with my 18. And I'm going to add on the subtraction, the original temperature of the T minus the surrounding temperature. We'll be doing that subtraction in a minute. You can just do it in your head, but I'm going to write out what the values are so we can see where everything is coming from in this formula. Now my E has an exponent of negative K multiplied by T. Now, since we have some information, I'm going to plug that information into my formula. We know that T of 2 is equal to 18 plus, now let's go ahead and subtract 90 minus 18, and that, of course, is giving me 72 e to the negative k multiplied by the time that it took to get to the temperature of 65 degrees. That was 2 minutes. And that answer has to turn out to be 65 because that's the temperature after 2 minutes. So our goal then is to be able to evaluate this constant K in my formula. Now we've worked quite a bit in the past few days with solving exponential equations, and usually we're going to have to log both sides. So let's go ahead and simplify this equation so that we can isolate the K and solve for it. So the first step is going to be to subtract 18 from both sides of the equation. That 18 is just being added, so the inverse operation would be subtraction. So I now have 72 e to the negative, I can just as easily write this as 2k, is equal to 65 minus 18, which gives me 47. Now I again want to isolate that exponential, so I'm going to divide both sides of the equation by 72. Now obviously this is a pretty complicated equation to solve, so you're going to have to think about the steps here in getting that variable by itself. So I've got e to the negative 2k is equal to, now this is where it's up to you. You can do the division of 47 divided by 72 and store that decimal, or you can leave it in fraction form, 47 over 72, and not have to worry about carrying out a whole big decimal. Again, it's okay to also divide and store that decimal. So the next thing that I would like to do, because I've got a base of e, to solve this for k, I'm going to natural log both sides of the equation. I'm choosing natural log because natural log and e are inverse functions. So every time I've got an exponential with a base of e, the best way to get rid of that e is to take the natural log of both sides. So whenever I have an exponent on a log of an exponential, I'm going to bring that exponent down in front. So I have negative 2k, natural log of e, equals the natural log of 47 over 72. Now to finish this off, we of course know that the natural log of e is equal to 1. So I now have negative 2k times 1 equals the natural log of 47 over 72. To get the k by itself, I'm going to divide both sides by negative 2, and then I'm going to go to my calculator. So I'll have the natural log of 47 divided by 72, all divided by negative 2. So this is where I go to my calculator and I do the natural log, parentheses, 47 divided by 72, close parentheses, divided by -2. That's giving me as my k to the nearest 10 thousandths 0.2133. Now it's a good idea to go back and check that by substituting that value in for k back here, entering the whole left side of your equation with that value in for k, and making sure that my equation does equal 65. So, to recap, in part B, the equation that we are now using, the function that represents the temperature of the tea, would be T of t is equal to 18 plus 72 e to the negative, here comes my k value, 0.2133 multiplied by whatever the t is. So for any amount of time, I can now use this formula. So in part C, to find the temperature of the tea to the nearest tenths after 15 minutes, I can say T of 15 is equal to 18 plus 72 e to the negative 0.2133 multiplied by 15. So again, let's go to our calculator. We are never, ever, ever going to just say 18 plus 72. When I'm given a complicated expression like this, I am going to literally type it into my calculator just like I've got it written right there. I want to find the temperature of the tea to the nearest tenth, so enter that value into your calculator. And again, pause the video if you need to take a few minutes to enter it. And I got for my answer 20.9, and my units would of course be degrees Celsius. Now, while you're working with your graphing calculator, let's enter the function that we just wrote down in part B into the y1 in your graphing calculator. We want to graph this on the interval from 0 to 60, so I'm going to set up my grid and I'm going to make a table of values. For my table of values, it would make sense to make my t, of course, the independent variable and capital T the dependent variable. Since I'm going from 0 to 60, I think it makes sense to count by tens. So do that on your table of values as well. Now pause the video for a few minutes, set up your axes on paper and also on your graphing calculator, and then make your table of values, fill it in, and get the points. Come back and check your answer with my answer and see if your graph matches, and we'll talk about the graph. Hi, take a look at my table of values and you'll notice that the temperature starts at 90 degrees. That's what we expected because that was the temperature of the tea. And then it cools down very rapidly because in the first 10 minutes it's already down to 26.5 degrees. We notice that as time goes on, 30, 40, 50, and 60 minutes, we see that the temperature approaches 18 degrees, which is of course the surrounding temperature. The temperature of the tea can't go below what the surrounding temperature is. There's nothing to make it go colder than 18. So I've added a horizontal asymptote on my graph at y equals 18. You'll see that as a dotted line. When I plotted the points, I could see that pretty quickly those dots came closer and closer to that answer of 18. Technically, this isn't even a horizontal asymptote because the temperature does reach 18 degrees. So let's go back and recap here. The maximum temperature of the tea is going to be the temperature that it started at, and that's 90 degrees. We could have also calculated that by finding the temperature at time 0, plugging that into our equation. The minimum temperature is going to be the temperature of the surroundings, so that one is going to be 18 degrees. It can't go lower than what the surroundings are. Let's turn the page and try a pizza problem next. So you'll remember that I said most often this formula is applied to liquids, but very often we do talk about anything that can be cooked, in this case a pizza. We have heated up our pizza, and the pizza was in an oven that had a temperature of 400 degrees. So since the pizza is coming out of the oven, we're going to say that the pizza is starting at 400 degrees. So I'm going to write that down as one of my variables. TO is going to be 400 degrees Fahrenheit because that's the original temperature of the pizza. It's placed in a 75-degree room. Notice that this example is written in terms of Fahrenheit. So my surroundings, this time 75 degrees. And that is happening at time t equals 0. Now, the temperature of the pizza is changing such that this time I'm given the decay constant. So K is equal to 0.325. That'll be important in setting up our equation. And this time the question is saying, what amount of time does it take for us to get my pizza down to 150 degrees so that I can go ahead and eat it? So solve algebraically, and we're going to round to the nearest tenth of a minute. So let's make our equation. So we know that T of T is equal to the temperature of the surroundings, 75, plus the original temperature of the pizza, 400, minus the temperature of the surroundings, 75, e to the, and this time we can go right ahead and put our K value into our equation, so negative 0.325 times T. Now we want to know when this answer is going to be equal to 150. So let's do some simplification here first so that we can solve. So 75 plus 325, e to the negative 0.325 t is equal to 150. Our first step is to subtract that 75 from both sides of the equation. And when we do that, we now have 325 e to the negative 0.325 times t is equal to 75. Now let's divide both sides of the equation by 325 because I want to isolate the exponential. And this one does turn out to be a decimal. I'm going to write it as the decimal. You could also reduce the fraction if you prefer. So I can say e to the negative 0.325 t is equal to, that decimal turned out to be 0.230769. I'm going to put ... on my paper showing that there's more decimal places there, but I'm going to store that answer in my calculator so that I can call it up later. Now, because I'm trying to solve for the t in the equation, I need to get rid of the base e, so I'm going to take the natural log on both sides of the equation. When I do that, that exponent comes down in front because that's one of our exponent properties for logs. So negative 0.325t times the natural log of e is equal to the natural log of 0.230769, that number that I have stored in my calculator. Again, remember that the natural log of e is just equal to 1. So I want to divide both sides by negative 0.325 to get the t by itself. So I don't really normally go to my calculator until I've got the t by itself. So t is equal to the natural log of 0.230769 ... all divided by, not a log, but divided by negative 0.325. So on my calculator, I'm going to use the natural log key of that number that I stored in my calculator, close off the parentheses, and then divide by negative 0.325. So be very careful how you enter this in your calculator. If you're having trouble getting the same answer that I'm getting, please see me so that we can look at it on your calculator. So this tells me that I'm going to have to wait 4.5 minutes to eat my pizza so that it has cooled off enough so that I don't burn my mouth. So 4.5 minutes is our answer. Look over that simplification and how we solved for the time, especially watching the part where we took the natural log on both sides of the equation. Let's try one more example. We're going to go on to a cup of coffee. So in problem number 3, our cup of coffee has a temperature modeled by, notice that I'm given the equation this time. It's in the same form as the one that we've been looking at all along in this lesson. And what we want to do is find the temperature of the coffee at the beginning of the experiment. Beginning, when we're talking about experiments like this, just means at time 0. So I want to substitute 0 in for my time. So I'm going to say 112 e to the negative 0.08 times 0 plus 68. Now if you look at that carefully, this part right here is just a number raised to a 0. Anytime I have a number raised to a 0, that value is just going to be 1. So I really have 112 times 1 plus 68. Adding those two values together, I see that my coffee is starting at 180 degrees Fahrenheit. Now if I look at the equation, it's easy to see that the temperature of the room must be this number right here, that's 68 degrees. It also makes sense because 112 represents the difference between the temperature of the coffee to begin with and the temperature of the surroundings. So if I were to do 180 minus 68, that's where that number 112 came from in my equation. Now, the trickiest part, the real Algebra 2 question here is, let's find the number of minutes when the temperature of the coffee is 140 degrees. So let's take our equation, 112 e to the negative 0.08 t plus 68, and set that equal to 140. Just like before, we want to get the exponential by itself, so let's subtract 68 from both sides of the equation. So we now have 112 e to the negative 0.08 t is equal to 140 minus 68, 72. Now I want to get the exponential by itself, so we divide both sides of the equation by 112. So I now have e to the negative 0.08 t is equal to, and again I did this as a decimal and then I stored it in my calculator, so 0.64, 2857, etc. I want to solve for t, so I'm going to take the natural log on both sides of the equation. That allows me to move that exponent down in front. So I now have negative 0.08 t times the natural log of e is equal to the natural log of 0.642857, etc. Natural log of e is 1, so I just have to divide by negative 0.08 on both sides to get t by itself. So go to my calculator. Natural log of 0.642857, so I'm hitting natural log and then the variable where I've stored that decimal. Close the parentheses and divide by negative 0.08. We want this to the nearest thousandth, so that's 3 decimal places. I got 5.523 minutes. Now again, notice that it's very, very important that you not round anything until you get to your final answer. So that tells me don't round this decimal right here. Make sure you're using all the decimal places that show up on your calculator. If you have any questions with that formula or how to use it to find the time, please come and see me in the morning. Let's go ahead and finish this example with part D, where we want to find the temperature of the coffee after 10 minutes. This is usually the easier part of the problem because we just want to be able to plug 10 into the function for our time. So we're going to say 112 e to the negative 0.08 multiplied by 10 plus 68. Notice that when I've got that plus 68 in my function, that's the vertical shift in my exponential function. So that means we've taken our whole exponential function and shifted it up 68 units. Now let's go ahead and put this into our calculator to get the answer. So when I entered that whole expression, and again, I'm not doing it piece by piece, I'm entering the whole thing, I got as my answer 118.3 degrees Fahrenheit. So I see that the temperature of my coffee went from a beginning temperature of 180 degrees. After 10 minutes, it had dropped all the way down to 118 degrees. And again, that answer makes sense because think about what happens when you bring your coffee to a cooler place. This time we were just putting it in our cooler room, 68 degrees. So thanks for working with me on the Newton's Law of Cooling problems. We're going to be practicing some of these as well as some other problems so that we're ready for our test that's coming up. So we'll see you tomorrow at school. If you have any questions, please come and see me so that we can get those cleared up. Have a great night. We'll see you tomorrow.